Hi, welcome everyone. My name is Idan, and I will present our work on ranking urban similarity using aerial image. This is a joint research effort within Google Research, was published in WACRI this year, as you already know. Here we tackle a real-world problem. Figure out how much work it will take to map a brand new city. We needed to know if our current models could handle it, or if we could head to collect new data and start training all over again. The standard way of estimate this using the out of distribution approach is to bias through a specific model. So I'm sorry. So we realized that we needed a better, more general way to measure just how different two cities actually are. Current model approaches treat urban scenes as one big uniform picture. While they are good at finding distinguished objects, they fail to see the fine-grained details that separate one city from another. We decided to use constructive learning to map out those general urban similarity. Our main goal was to build a framework that know exactly where and how to look for fine-grained structural difference to discover the city DNA. Cities look very different around the world due to culture, geography, and local rules. Standard models struggle to separate meaningful structural changes from a random visual noise. We decided to focus on core variations, road topology, infrastructures difference, and unique marking convention. To solve this, we created a three-stage pipeline. Stage one is retrieval, where we automatically extract specific aerial image patches. Stage two is constructive adaptive learning, where we train a model, a joint embedding space. Stage three is ranking, where we classify city pairs and generate a final similarity score. We built a global diverse dataset without any manual labeling. We selected the 33 geographically diverse cities and focused on 30 different infrastructure types. By using a vision language model, a CLIP style, we search our database using a simple text prompt like aerial view of a roundabout. This gave us more than 1.5 million samples covering varied areas around the world. For the second stage, we created a type awareness by fusing image text encoder by fusing image and text encoder together. An image encoder extracts the visual features, while frozen text encoder processes the name of the infrastructure type. A lightweight transformer fuses those two inputs together. This allows the model to focus on relevant visual clues, mutual information, without needing us to train 30 separate models. However, we notice an imbalance during training. Not all types are equally helpful. Intersections, for example, give us strong clue about the city, but the narrow streets can just be noisy. If we are not careful, the weak features will water down the training signal. So we introduced an adaptive mechanism to dynamically prioritize the most helpful type. The system calculates a separation score based on how well a type distinguishes cities. Then we normalize those scores, and finally, the system automatically boosts highly discriminative types and suppress noisy ones during training. In the final stage, we extract pairwise visual similarities between images. A binary classifier predicts the probability that two images comes from the same city. By aggregating this prediction across every combination, we generate a dense global city-to-city similarity matrix on the right. We found that the model performs much better when telling exactly what type is looking at. This is the second column over here. On top of it, our adaptive training improves even more by focusing on the most helpful features. This is on the right. For example, features like intersection and traffic island are varied in their separability power. When we visualize the data, we see a compact city-specific clusters forming within a single road categories. On the left, crosswalk. On the right, pedestrians. Interesting city that drive on the left side of the road naturally cluster closer together based purely on their medians. This is the cluster over here. This proves the model successfully captures functional design. We can look at the feature importance score, and we see exactly which feature drive the model. Residential grids, stop lines, and medians provide the vast majority of the signal for separating city, whereas, for example, narrow street feature is almost not used in the classification. The model achieved a high AUC score on unseen data, confirming those features translate into effective real-world discrimination. Then we ask if our visual score match a real-world attributes. Yes, the model showing a strong alignment with economic scale, as everything is about the money. However, it shows a weak or not alignment with other factors like climate, density, or age of the cities. We compare our result to a standard map. Sure, neighboring cities often look alike, but our model successfully groups cities that are thousands of kilometers apart if they share the same urban design. The big takeaway is that structure beats location. Our models know that, I'm sorry, our model knows that just because two cities are close together, it does not mean they are built on the same way. An interesting example is Vienna. Vienna is over here, is much closer to London, but have a better similarity score to Madrid, which is far more than London. Treating city as a single solid blocks causes us to miss the important details. By zooming in specific road types and using better training, we cut through the noise to see how city truly built. Most importantly, this gave us the exact tool we need to measure city similarity and estimate the effort for future mapping work. And that's it.